Hey everybody, this video lesson is going to talk about the concepts of resonance structures of Lewis dot structures and formal charge, and using formal charge to determine which resonance structure is preferred over the others. Now to lead off this conversation, I want to point out this first bullet point. It's a question that I posed to you. What happens when a Lewis dot structure, and that's what LDS stands for, is Lewis dot structure, can be drawn two or more correct ways? In other words, you followed all the rules of drawing Lewis dot structures. You've placed all the electrons appropriately, but there's more than one way in which that Lewis dot structure can be drawn. Before we discuss that concept and resonance, I want to talk a little bit about the idea of an isomer. An isomer is a formula that's the same as another formula, but the molecules are completely different because the order of the elements and the bonds are different. This most often shows up in an organic chemistry course. Essentially, one formula could apply to two different molecules, and those two molecules have different properties. I'm going to use in the example of C3H7OH. Now, depending on how you organize these atoms, you come up with two distinct structures. Here's the first one with 3 carbons in a row. And in fact, both structures have a backbone of 3 carbons in a row. Now, off of each carbon, there's going to be a single bond. So we look like this. Now we're going to place the 7 hydrogens starting from the left-hand carbon and placing the hydrogens. So there's 3, 4, 5, 6, 7. And then we place the O bonded to the H on the end. The OH in organic chemistry is an alcohol functional group. Essentially anything with an OH on it is considered an alcohol in the eyes of an organic chemist. Now let's take the same carbon backbone of 3 carbons in a row. And instead of placing the OH on the end, we place the OH on the central carbon rather than one of the end carbons. And then what you get is another form of C3H7OH. The one on the left is known as propanol, and this one on the right is known as isopropyl alcohol. And the iso means that the OH is on the central atom, where if you just call it propanol or propyl alcohol, it's on one of the end carbons. These two molecules are not resonance structures because the order of the elements changed and the bonds are different. We call these isomers of one another. But resonance, on the other hand, is the order of the elements remain the exact same and the electrons just change their position. Usually there's a central atom with multiple ligands, and you're looking at single, double, and triple bonds changing between the central atom and the ligand. So we're going to take a look at resonance right here on this next page. What you're looking at are 3 different structures, but in fact they all represent the same molecule, NO3, or the nitrate polyatomic ion. Now if I ask 3 different people to draw the polyatomic ion nitrate, 3 different people may come up with 3 different structures. One where the double bond's on the bottom, one where it's in the upper left-hand corner, and one where it's in the upper right-hand corner. And you'd ask yourself which one of these structures is preferred. In fact, the actual structure is an average of all the known resonance structures of that substance. In other words, you can think of it like this. Nitrogen's in the middle and there's 3 oxygens or 3 ligands. In nitrate, there needs to be 4 bonds spread out between 3 ligands. And if you do that in an even way, you get these 3 distinct resonance structures. We treat them all equally, like they're all representing the same atom, or the same molecule, I should say. And so we draw double-sided arrows in between the 3 resonance structures to say, hey, all 3 of these are equally likely to occur. In fact, you could even apply like a fraction. 1/3 of the time it looks like that, 1/3 of the time it looks like the one in the middle, and 1/3 of the time it looks like the one on the right. The electrons we draw as static, but in reality the electrons are moving around the outside of the central atom so quickly that at any given time the electrons could be here or here or here, depending on the time which you look at it. Think of this concept because we always draw electrons as static, but in fact we say that they are delocalized, meaning they have no home. They don't have a spot where they're always located. They flow around the entire molecule between the bonds and the pairs of electrons. If you think of a molecule like a violin string or a guitar string, and you pluck the string, and as you look at it, you see the string vibrating. And that's kind of where the word resonance comes from, because strings resonate with sound just as electrons resonate around the different atoms of a molecule. So if you look at a violin string that has been plucked and you look at the vibrating string, you don't really see one string, you see many, many strings all at the same time. That's similar to what you would look at if you saw a molecule with its electrons resonating. You wouldn't see one of these three structures, but you would really see all three happening at the same time. Or a fan that's spinning. When the fan's spinning, you don't see the individual blades of the fan, but rather you see one large circle of fan. Only once you turn it off are you able to identify the different blades. That's what the different bonds, and in this case the double bond, is doing, is it's spinning or resonating around the different areas of bonding in a molecule. So let's try this molecule, SCN. And I'm going to draw them out for you here so that you can see how I do it. Now SCN, when carbon's in a molecule, it's usually in the center. So you can write carbon in the middle, and you can write N on one side and S on another. Now before we go any further, it's probably best if we add up our electron bank. Sulfur has 6 electrons valence, carbon has 4 valence electrons, and nitrogen has 5 valence electrons, and then we need to account for the extra electron because it's a polyatomic ion. So you're looking at 16 total electrons in the bank. Now with 2 single bonds, I subtract 4 from the bank, which leaves me now 12 dots to distribute around the outside working in. And so I'll do that. I'll put 12 dots, which is 6 pairs of dots around the sulfur and the nitrogen. Now what happens next is I start to grab electrons from the outside and share to the carbon, because as I check my different elements in the resonance structure, or I guess in the Lewis dot structure, the outsides have 8, but the inside doesn't, and we need to satisfy the octet rule, as we talked about in a previous video lesson. So you need to share pairs of electrons from the outside. So I'm going to erase a pair of electrons from each of the outside elements and make double bonds to the central atom. Now on the other hand, I could have done it a little bit differently. If I had my 12 electrons on the outside, and instead of taking away 2 from each side, maybe I take away 2 sets from one side and make a triple bond, leaving one side single bonded. And then the other option would be as if I triple bonded the sulfur side and single bonded the nitrogen side. So these 3 are equivalent resonance structures, or I shouldn't say equivalent, we'll get to that here in a second, but these are 3 possible resonance structures of the molecule SCN. To finish them off, it's best if you put them in brackets with the charge of the ion on the outside. Now, I mentioned the word equivalent or lack thereof because these 3 resonance structures of SCN are in fact not equivalent to one another. Equivalent resonance structures have the exact same element as ligands, but this molecule has different elements as ligands. So these 3 structures are not equivalent to one another. And they're not equivalent because the bonds on either side of carbon are not equal. In fact, if we were to determine the bond dipole on each side, we would use an arrow and we would use a vector to show that nitrogen, in fact, is pulling harder on the electrons than sulfur is. In each one of these cases, sulfur has a smaller vector than nitrogen because nitrogen's more electronegative. So this molecule is polar, and polar molecules usually don't have equivalent resonance structures due to the differences in electronegativity of the ligands of the molecule. So if these 3 resonance structures of SCN, which should have double arrows between them, are not equivalent, then which of these is the preferred resonance structure over the other 2? Going back to my example on the last slide, the NO3, the oxygen, was equivalent in all 3 resonance structures, if you remember. So the pull between oxygen and the nitrogen in the center were equal on all 3 resonance structures. But in this situation, the sulfur and the nitrogen do not have equal pull on the electrons. And so we need a way to measure which of those 3 that you see in front of you are the, or is the, preferred resonance structure. And in order to do that, we need to use something called formal charge. Formal charge is a quick calculation that you can use to evaluate non-equivalent Lewis dot structures like the ones that I just had on the last page. In order to calculate the formal charge, what you do for each element in a Lewis dot structure, you take the valence electrons that that element has normally, subtract the number of bonds it has touching it, and then also subtract the pairs of electrons, individual electrons, from that total. Ultimately, atoms are trying to achieve a formal charge as close to zero as possible. And if all the elements have a zero formal charge, then that's the preferred resonance structure of that Lewis dot structure. But if there ever is a situation where one or more of the elements carries a formal charge, then we need to decide using a couple of set of sub-rules to determine which is the preferred Lewis dot structure. The first rule, or the overarching rule, the one that governs the whole shebang here, is that atoms and molecules try to achieve formal charges as close to zero as possible. But if that's not possible, then we need to go to our next set of rules. So I'm going to redraw the three resonance structures that we built on the last page, and we're going to practice calculating the formal charge out for each one of the atoms in each one of these resonance structures, and then talk about what we're going to do from there. So let's start with the one on the left. Now I added the brackets and the charge for this polyatomic ion, and that is going to be a discussion point here shortly. But let's talk about the formal charge. Now let's start with carbon. Carbon has 4 valence normally, and I'm going to use red ink to determine or add up this valence. So 4 valence minus the total bonds, and since it's double bonded on both sides, that's 4 total bonds, because one bond is 1, double bonds are 2, triple bonds is 3. It has 0 dots, so its formal charge is 0. Now the sulfur normally has a valence of 6, and it currently has 2 bonds connected to it, and it has 4 dots, so its formal charge is also 0. Nitrogen, on the other hand, has normally 5 valence, and it's got 2 bonds and 4 dots, so right now it's carrying a formal charge of -1. Now the resonance structure in the middle, let's do the same thing. Carbon has 4 valence minus 4 bonds minus 0 dots, so it's 0. Let's do the sulfur. 6 valence minus 1 bond minus 6 dots, or it's got a -1. Nitrogen has 5 valence minus 3 bonds minus 2 dots, so now it's 0. See, by shifting the double bonds evenly, as you can see, to a triple bond and a single bond, you've changed the formal charges of the elements. On the one on the left here, the nitrogen had the -1 formal charge, and on the one on the center here, the sulfur has the -1 formal charge. Now let's finish up by doing this one over here. Carbon, once again, 4 valence minus 4 bonds minus 0, so it's 0. Sulfur has 6 valence minus 3 bonds minus 2 dots, or a +1 charge, and the one on the right, the nitrogen, has 5 valence minus 6 dots minus 1 bond. And I should do it in order, just so you don't get confused. So it's 5 valence minus 1 dot minus 6 electrons for a -1. Actually, this should be a -2, right? 5 minus 1 is 4, minus 6 is -2. So you've got 3 resonance structures, each with their formal charges determined. Let's talk about the follow-up rules now. The first sub-rule is that the sum of the formal charges in a resonance structure has to equal the ion charge. If you've got a neutral molecule, then the formal charges should add up to be 0. But in this case, since we have a polyatomic ion of -1, the formal charges have to add up to -1. It does in this first one, it does in this second one, and +1 minus 2 gives you a -1, does in this third one. Now, the rule that you talked about, or we talked about on the previous slide, is that elements prefer to have a 0 formal charge as much as possible. Now this last one on the right actually has 2 atoms with a formal charge, and so that right there is going to disqualify this one compared to the other 2. The other 2 have 2 zeros and a -1 formal charge on the 3 atoms respectively. So we need to decide which one is going to have the -1 formal charge assigned to it. And whatever that one is going to be the preferred resonance structure. So the second rule is that Lewis dot structures are preferred with negative formal charges on the most electronegative element. Now I would have to tell you the numerical value of these two, but I'll tell you right now that nitrogen is more electronegative than sulfur, and so the formal charge of -1 should be applied to the nitrogen, and in this case, the first resonance structure is the preferred resonance structure of these three options. So I'll double or triple underline this one, tossing out the other two. You would use formal charge to determine the preferred resonance structure if you have non-equivalent resonance structures, like in this case. To summarize the rules, the first rule is the most important rule, that elements want to be as close to zero as possible. If that's not possible, then you assign the negative formal charge on the most electronegative element, and then that is the preferred Lewis dot structure. And finally, double check that the sum of the formal charges is equal to the ion charge. Otherwise, you added something up wrong. Let's take a look at practicing assigning formal charges for another molecule, as you can see. We're looking at POCl3. Now let's assign the formal charge to each element. So let's start with the middle. Phosphorus has a valence of 5, and it's got 4 bonds and 0 dots, or a +1 charge. Now, the oxygen has 6 valence normally, and it's got 1 bond minus 6 dots, or a -1. And finally, the chlorines, which are all identical to one another, so you only have to do this one time if you have the same chlorine 3 times. Then you've got chlorine, which is a halogen, so they have 7 minus 1 dot minus 6 dots, 1 bond minus 6 dots equals 0. Now, since this is a neutral molecule, the formal charges should add up to equal 0, so that's good. It does, so we don't need to worry about that. And since there's only one resonance structure of this Lewis dot structure showing to you, then you can assume that this is the preferred resonance structure. But I pose to you this question: is there a possible way to shift around the electrons in this molecule, keeping in mind that phosphorus can actually expand its octet and have more than 8 surrounding it in a molecule? So let's think about it. If we could shift around a pair of electrons to make a double bond out of phosphorus with one of the ligands, is there a way to eliminate the formal charge on the phosphorus and the oxygen? And to be honest, those are the two elements you should be worried about. You don't want to mess around with the chlorines because they're already at a 0 formal charge. So what I'm going to do is say, all right, let's take this and eliminate 2 of these electrons and make a double bond out of it between oxygen and phosphorus. Now let's recalculate the formal charge of the phosphorus. Phosphorus has 5 valence, now minus 5 bonds, minus 0 dots, or formal charge is 0. Hey, we're on to something here. Next, oxygen, which has 6 valence, now has 2 bonds and 4 dots, so its formal charge is 0. And chlorine still remains 7 minus 1 bond minus 6 dots, so 0. So in fact, the original structure of POCl3 is not the preferred resonance structure. It was just the one that was represented to you. But in fact, if you were able to, and you were asked to rearrange the electrons of POCl3 to eliminate formal charges, this would be the preferred structure. Now that's only possible if phosphorus or sulfur in the middle, or the central atom is something 3rd energy level or lower. Because remember, those are the only elements that can expand their octet. Carbon and nitrogen and oxygen would just have to be stuck with a +1 and a -1 situation, but phosphorus is a special case. Finally, we're going to end this video lesson talking about an actual problem from the 2018 test, and this is a Lewis dot structure and sprinkles in formal charge and resonance with it as well. It says the skeletal structure of HNO2 molecule is shown in the box below. And they asked you, they being the college and the test creators, asked you to complete the Lewis dot diagram of HNO2 molecule in the box below, including any lone pairs of electrons. So they give you the order in which the elements occur, and you have to come up with the proper Lewis dot structure. Now, there's going to be 2 options, so might as well draw the second one below it, and then we're going to decide between them. But let's generate our bank. H is a 1, N is a 5, and you've got oxygen twice. So 6 plus 6 is 12, plus 5 is 17, plus 1 is 18. So you have 18 in your bank. Now let's start putting in single bonds between these 3 elements. So subtract 6, leaving you now with 12 dots. Now the dots can't go on hydrogen because it's full at a duet. But you can start putting on electrons are on the outside elements. Oxygen takes 6, 7, 8, 9, 10, 11, 12. Now we need to decide. We need to double bond the oxygen to the nitrogen. Now, on the one hand, I'm going to take a pair of electrons off the outside right element and make a double bond with the nitrogen to oxygen. But another situation would have a double bond between the oxygen and nitrogen in the center. And so the Lewis dot structure would look something more like this. Now, these are the two possible resonance structures of HNO2. But you need to use formal charges now to determine which one of these is going to be more likely. And if they both happen to have formal charges that are near identical to one another, then really it doesn't matter. But let's take a closer look at the formal charges of each one of these elements that make up HNO2 in each resonance structure. So first of all, let's go to a new color here, like red. So hydrogen has 1 valence minus 1 bond minus 0 dots, so it's a 0. The first oxygen, and there are two of them, the inside oxygen and the outside oxygen. The first oxygen has 6 valence minus 2 bonds minus 4 dots. In other words, it's 0. The other oxygen is 6 valence minus 2 bonds minus 4 dots, so it's 0. And finally, the nitrogen is 5 valence minus 3 bonds minus 2 dots, or 0 as well. So it looks like all of these are 0, so that might be the preferred resonance structure. Let's take a look, just for the sake of comparison, of these on the bottom. Hydrogen, once again, has 1 minus 1 bond minus 0 dots for 0. So the inside oxygen now has 6 valence minus 3 bonds minus 2 dots, or a +1 formal charge. Not ideal. The other oxygen has 6 valence minus 1 bond minus 6 dots, or a -1 formal charge, and the nitrogen remains 5 valence minus 3 bonds minus 2 dots. So you're looking at the one on the top versus the one on the bottom, and the one on the top has all formal charges of 0, where the one on the bottom has a +1 and a -1. In some cases that's okay, but in this case, this is a better resonance structure. And so you could simply just cross this one out and say this is the preferred resonance structure based on the formal charges of the elements. Well, hopefully you picked up a little bit about resonance, and specifically using formal charge to determine which resonance structure is preferred when resonance structures are non-equivalent. That takes care of this video lesson. Thanks for listening.